Exercise 1531 is asking you to calculate the degree of unsaturation for each of the following molecular formulas. So the saturation here is referring to hydrogens. Something is saturated if it has as much as it possibly could have on it. And molecules, carbon chains, are saturated if they have as many hydrogens as they possibly could have. They're unsaturated if there are places where instead of having hydrogens, you have bonds to other things. For example, you could have double bonds between carbons. This is a bond on each of these carbons that could be going to a hydrogen. So you don't have as many hydrogens as you could have, theoretically, if you have a double bond. Or if you have a ring, this bond here between the carbons, if it were a straight chain, that could be a bond to two other hydrogens. So by forming a ring, you also take away a spot for hydrogens, and the molecule has less hydrogens than it possibly could have. It's unsaturated. So what the degree of unsaturation ends up meaning is how many double bonds or rings you have. A 1 degree of unsaturation means you'd either have one double bond or one pi bond or one ring. 2 degrees of unsaturation means you either have 2 pi bonds, 2 rings, or 1 pi bond and 1 ring, and so on and so forth. The unsaturation here, interestingly, is the same word, the same concept as later will be used to describe fatty acids, so that fats will either be able to be saturated or unsaturated based on whether they have as many hydrogens as they possibly could have, in the case of saturated fats, or whether they have places where they have pi bonds, or theoretically rings. Those are unsaturated fats. So you can figure out the degree of unsaturation. So that's what the degree of unsaturation is. And it's useful because we saw earlier how you could come up with a plausible molecular formula just using the mass spectrum, using the different isotopes of carbon, the relative abundance of it. So you can come up with a molecular formula, but if you wanted to draw the molecule, it would be difficult to know how to fit all the atoms together. And this degree of unsaturation, knowing how many pi bonds and how many rings you have, helps you to go from the molecular formula to the shape. So that's why it's useful. It's also really easy to get. Now, if you're strapped for time, you could just use this equation. You could follow this equation and go through each one of these and find the degree of unsaturation. Incidentally, the degree of unsaturation is synonymous with the hydrogen deficiency index. Remember, this is how many hydrogens you're missing, right? A molecule is saturated if it has as many hydrogens as it could have. If it's unsaturated, it has less than that. In other words, it's deficient in hydrogens by a certain amount. So the hydrogen deficiency index is synonymous with the degrees of unsaturation. Now, if you are just plugging these numbers in, just keep in mind C is the number of carbons, N is the number of nitrogens, H is the number of hydrogens, and X is the number of halogens. That would be chlorines, bromines, iodines, or if you have them, fluorines. So you could just do that. We'll end up doing that in a second. First, I want to show you where this formula is coming from. This portion of the formula in orange, that is the maximum, that's a calculation for the maximum number of hydrogens in a molecule. Let's think about why. If you have a carbon chain with all single bonds, then you could have, first, twice as many hydrogens, one going up and one going down, twice as many hydrogens as carbons, then plus the 2 on the end. So 2 plus 2. 2 carbons plus 2. That's the maximum number of hydrogens you can have coming from carbon. If there's a nitrogen on the molecule, notice what happens. You replace the position of one hydrogen with 2 positions for hydrogen. So the one you took away and the one of the ones you add, those even out. You end up adding a net 1 hydrogen when you add a nitrogen. So each nitrogen ends up adding 1 hydrogen. A similar thing doesn't happen with other elements. For example, if I put an oxygen there, that takes away a bond to a hydrogen, but oxygen can form another bond to a hydrogen. So it evens out. Okay, so that's where this 2 times the number of carbons plus 2 plus the number of nitrogens is coming from. That's the maximum number of hydrogens in the molecule. And then this here is the actual number of hydrogens in a molecule. Now, technically, the number of hydrogens is just what the H is standing for. The X is standing for a halogen, so fluorine, chlorine, bromine, or iodine, because halogens act a lot like hydrogens. If we have that carbon chain, you could imagine having a hydrogen at any end of these. But if a halogen were at the end, so like a chlorine were at the end, you'd still have the same number of single bonds. You wouldn't have any double bonds or rings there. So a halogen ends up kind of acting like kind of like acting like a hydrogen, acting like a substitute for a hydrogen. So if we're interested in finding the number of double bonds or rings, what we're going to do is we're going to take the maximum number of hydrogens and compare that with the actual number of hydrogens. Okay. Now notice what happens when you take hydrogens away to form a double bond. In order to form a double bond, you have to get rid of 2 hydrogens. If I want to form a double bond between these carbons, I have to get rid of 2 hydrogens. Likewise, if I wanted to form a ring, let's say I wanted to put all these carbons in a ring, I would have to get rid of 2 carbons, the ones on the end, so that the 2 hydrogens, I mean. I would have to get rid of 2 hydrogens, the ones on the end, so that the carbons connect with each other. In other words, every 2 hydrogens, I should say, 2 missing hydrogens is the same as 1 pi bond, or 1 ring. So if you have a certain number of missing hydrogens, just divide that by 2, and you'll get the number of bonds or rings. And that's what this 1/2 is there for. It's to take the number of missing hydrogens and divide it by 2 so that you get the number of bonds or rings. Okay, so you see how many hydrogens you have, you see the maximum number of hydrogens you have, you see the actual number of hydrogens you have. That lets you figure out how many you're missing, and then you just divide that by 2, and that gives you the number of pi bonds or rings in your molecule. Okay, so now that we have derived that equation, seen where it comes from, let's apply it. So we have this equation. First, let's apply it to this formula right there. So this molecule, the hydrogen deficiency index for this is going to be 1/2 times 2 times 6 plus 2. There are no nitrogens, so plus 0, minus the number of hydrogens, there are 10 of these, and then minus the number of halogens, there are 0 halogens in this. So that's 1/2 times 12 plus 2 minus 10, or 1/2 times 14 minus 10. Okay, so 1/2 times 4, or 2. So the hydrogen deficiency index, the degree of unsaturation in this molecule, is 2. That means in this molecule we either have 2 rings or 2 pi bonds or 1 ring and 1 pi bond. And that would help us draw that molecule, or at least draw possible shapes for that molecule. Okay, so we're going to use that equation again. And actually, we'll plug it in. So here, the hydrogen deficiency index will equal 1/2 times 2 times the number of carbons, so that's 5. Plus 2, plus the number of nitrogens, which is 0, 0 in this molecule, minus the number of hydrogens, which is 10, and minus the number of halogens, fluorine, chlorine, bromine, or iodine, which is 0. Notice the oxygens don't affect the number of hydrogens, because the bond to the oxygen that it takes away from a hydrogen has, on the other side, just adds a hydrogen, so it evens out. So here, the hydrogen deficiency index will be 1/2 times 10 plus 2 minus 10, or 1/2 times 2, or just 1. And what that means is that this molecule has either 1 ring or 1 pi bond. Didn't take us long to figure that out, and it really helps us if we're trying to figure out the shape of that, or even the type of reactions it might be able to form. All right, let's keep going. Let's do this, apply this again to this right here. So the hydrogen deficiency index for this will equal 1/2 times 2 times the number of carbons, there are 5 carbons in this molecule, plus 2, plus the number of nitrogens, there is 1 nitrogen in this molecule, minus the number of hydrogens, which is 9, minus the number of halogens, which is 0. So that's going to be 1/2 times 10 plus 2 plus 1 minus 9, or 1/2 times 13 minus 9, or 1/2 times 4, or 2. And so what that means is that you have 2 rings or 2 pi bonds, or 1 ring and 1 pi bond. All right, we'll go down and apply that to this next one. So the hydrogen deficiency index here, or the degrees of unsaturation, are going to equal 1/2 times 2 times the number of carbons. We have 3 carbons. So 3 carbons plus 2. Remember, this is our formula that we're using. So this is our formula. Okay, so plus 2, plus the number of nitrogens. There are no nitrogens in this compound, minus the number of hydrogens. There are 5 hydrogens, minus the number of halogens. This chlorine is a halogen. We only have 1 of them, so minus 1. So the hydrogen deficiency index will be 1/2 times 6 plus 2 minus 6. So that's 1/2 times 2, or 1. And the meaning of that is that that molecule has 1 ring or 1 pi bond. Either one, but not both. Okay, so let's bring this down here, just so we have it for reference. That's our equation. So for this one, the degrees of unsaturation, or the hydrogen deficiency index, is 1/2 times 2 times the number of carbons, which here is 10, plus 2, plus the number of nitrogens, which is 0 here, minus the number of hydrogens, so 20, minus the number of halogens, which is 0. We don't have any fluorines, chlorines, bromines, or iodines. So it'll be 1/2 times 20 plus 2 minus 20. Well, that's 1/2 times 2, or 1. So here in this molecule again, there's either going to be one ring or one pi bond, but not both. All right, next molecule. The hydrogen deficiency index, or the degrees of unsaturation of this, is going to be 1/2 times 2 times the number of carbons. Here in this molecule, there are 4 carbons, plus 2, plus the number of nitrogens, which is 0, minus the number of hydrogens, which is 6, minus the number of halogens, fluorine, chlorine, bromine, or iodine. We have 2 bromines, so 2 halogens. So this is going to be 1/2 times 8 plus 2 minus 6 minus 2. That's 8 minus 8. So that's 1/2. Oops, sorry, 10 minus 8. 1/2 of 10 minus 8. 1/2 times 2, or 1. So the degrees of unsaturation are 1, and what that means is that you have one ring or one pi bond in that molecule, not both. Okay, so we'll take this formula, we'll just bring it down for reference. So we'll apply it to these. So this first one, G, so the degrees of unsaturation in that's going to equal 1/2 times 2 times the number of carbons, so that's 6, plus 2, plus the number of nitrogens, 0, minus the number of hydrogens, 6, minus the number of halogens, fluorine, chlorine, bromine, or iodine. We don't have any of those, so 0. Hydrogen deficiency index will be 1/2 times 12 plus 2 minus 6. So that's 1/2 times 14 minus 6, or 1/2 times 8. I'm sorry, 14 minus 6, yeah, 8. And so this will be 4. So this has 4 degrees of unsaturation. That means it either has it has 4 ways of combining pi bonds or lone pair or rings. So for example, you could have 4 pi bonds. You could have 3 pi bonds and 1 ring. You could have 2 pi bonds and 2 rings, or you could have 1 pi bond and 3 rings, or you could have 4 rings. So those are all ways of getting a hydrogen deficiency index of 4. One common molecule that has a hydrogen deficiency index of 4 is benzene. Benzene has 1 ring and 3 pi bonds. So that would be like this here. Okay. You can apply that same formula to these other compounds. So here in this one, in H, the hydrogen deficiency index is going to be 1/2 times 2 times the number of carbons, which is 2 here, plus 2, plus the number of nitrogens, 0, minus the number of hydrogens, 0, minus the number of halogens, halogens are fluorine, chlorine, bromine, or iodine. We have 6 chlorines, so minus 6. So this is going to be 1/2 4 plus 2 minus 6. That's 1/2 of 0, so 0. There are no rings and no pi bonds in this molecule. There's 0 degrees of unsaturation. Okay, moving on to I. The hydrogen deficiency index for this one is 1/2 times 2 times, we have 2 carbons here, plus 2, plus the number of nitrogens, we don't have any, minus the number of hydrogens, we've got 4, minus the number of halogens, fluorine, chlorine, bromine, or iodine, there are no halogens there, so 0. So this is going to be 1/2 times 4 plus 2 minus 4, or 1/2 times 6 minus 4. That's 1/2 times 2, or 1. And we've seen that if you have just 1 degree of unsaturation, that means that that molecule has either 1 pi bond or 1 ring. Okay, last but not least, let's find we'll go out with a bang. Let's find the hydrogen deficiency index of this crazy thing. So here, the hydrogen deficiency index, we can figure out exactly how many rings or pi bonds are in that by taking 1/2, 2 times the number of carbons. Here we have 100 carbons, plus 2, plus the number of nitrogens, we don't have any nitrogens, minus the number of hydrogens, we have 200 hydrogens, minus the number of halogens, we have 2 chlorines. And notice the oxygens don't make a difference. So here, the hydrogen deficiency index will be 1/2 times 200 plus 2 minus 200 minus 2. Well, that's just 1/2 times 0, and so 0. So look at that, in like 30 seconds we could tell that there are no pi bonds and no rings in that gigantic molecule. So really, this is a simple formula that you can use to find useful information, the number of pi bonds or rings in a molecule. Those are called the degrees of unsaturation, or the hydrogen deficiency index. And that helps you to go from molecular formulas to drawing